Hello and welcome to lesson 18. What I'm going to do today is derive the method of least squares. I could very easily give you the matrix equation to memorize, but I find that it's a lot easier to mess up the formula somehow when you don't know where it comes from. So that's what we're going to do. We're going to talk about where this equation comes from. So the star of today is the matrix, a matrix that is in some form of m by n, where m is greater than n. So what we know about this system, we actually know quite a bit about this system. And the other piece of information I'll give you is that A is full column rank. And so that means that R is equal to n. Okay, so what this means is that we have a system that's over-constrained. The other way that you can think of it is that there are more constraints than degrees of freedom. So think about what's happening here. So we have an input space, which is Rn, and our output space is Rm. And here's our column space of A transpose, column space of A, the null space of A, and the null space of A transpose. And if you are looking at the rank here, what you notice is that the dimension of the column space of A is going to be equal to n, as will the dimension of the column space of A. Okay, so the dimension of both the column spaces is n, and the dimension of the null space of A is equal to 0. So we won't have an infinite number of solutions in this problem because we don't have any free variables. So that's not a thing anymore. And then the dimension of the null space of A transpose now will be non-zero. Because if m is greater than n, m minus n is a non-zero value. And of course, what that means is that there will be either a unique solution or no solution at all. And what I want you to think about is, let's say m is equal to 8 and n is equal to 3. What you're talking about here is you're talking about a three-dimensional, there are three vectors, okay? So you have 3 columns that are trying to span an 8-dimensional space. And the odds of that actually happening, the odds of B being in the column space of A, are astronomically small. So what we are left to believe here is that the equation AX equals B cannot be satisfied exactly. Said another way, AX equals B has no solution. The alternative way we'd like to represent this, in math we often do this, is if I could also say that there is no X such that B minus AX equals 0. So usually, you know how sometimes when you try and make MATLAB prove, or you try and prove that two values are equal, you subtract them from each other and see if MATLAB gives you 0. This is sort of the same idea. So if there is no X that solves AX equals B, our options are either to give up, which I won't let you do, or use the method of least squares. So that is what we're going to do here. So what we're looking for, instead of forcing B minus AX to be 0, what if we relaxed the rules a little bit and said that we are just looking for B minus AX to be as small as possible, as close to 0 as we can? So what we're looking for is we're actually looking for the magnitude. So what we do is we seek an X such that the magnitude of B minus AX is as small as possible. Or we're trying to minimize B minus AX. So it's useful to name things. So what I'm going to do is name that vector. So let b minus ax equal r, where r is often what's called the residual or the error. Really, that's what this is. We're talking about the error. Okay, so what we're looking to try and do is make, or really we're trying to minimize r, or the magnitude of r anyway. Okay, so there are a couple ways that you can derive this. One of them is using a lot of matrix math, but what I'm going to do is show you geometrically what's going on here. So consider for a moment that we have a b that is not in the column space of A. And I talked about how this is statistically probable that we'll find a b that is not in the column space of A in an over-constrained problem. Okay, and what you notice here is, remember that from lesson 16 we talked about orthogonality. So the vectors that live in the column space of A are orthogonal to all the vectors that are in the null space of A transpose. And what we can do is we can represent this vector b as its components, just like we've done in the past with x homogeneous and x particular. Okay, so we're going to call the vector b that lives in the column space of A b star. And that's just the component of b that lives in the column space of A. And similarly, we can say that there's another component of b that lives in the null space of A transpose, and I'm going to call that r. Okay, and you know that the goal here is to try and minimize this vector r, and that makes sense, right? If I'm gonna use my little pointer, if r is smaller than b, less of b hangs into the null space of A transpose. And remember, any valid b can't have any component in the null space of A transpose. So when b gets smaller and smaller and smaller towards 0, then I'll have a vector that's completely in the column space of A. But what we're talking about is finding a vector r that is as small as humanly possible. And we're just trying to find this b star that is as close to b as we can. Okay, so what I can do here, what I'm going to do actually is I'm actually going to redraw the output space so you can see this this property a little bit easier. So I'm going to redraw this, and it's just a different perspective than our previous drawing. So the origin will be here, and I'm going to draw my vector b. So we'll pretend that this is a plane. Obviously that is not necessarily true, that the column space of A is just a plane, but it's easier to draw, so that's why I'm doing it. So let's just say that the column space of A looks like this plane, and my vector b does not live in the plane. It is some vector b that is, if you want to think of it, as hovering over the plane. Well, how do I find a vector in the column space of A that is as close as possible, or the magnitude of r is as small as possible, in order to find this value? Well, if you're thinking about projections, you're right. So if I could find a projection of b onto the column space of A, that lives in the column space, and the vector that is orthogonal to the projection is none other than my vector r. And you can see even clearer now that if r is 0, then b is in the column space of A. But if r is non-zero, then there is no solution to ax equals b. So the least square solution just says, okay, I'm just trying to find a vector, the projection of b onto the column space of A that is as close as possible, i.e. the magnitude of r is as small as possible. Okay, and I'm going to name this vector, this projection of b onto the column space of A, b star. Okay, so we know a couple things now. So if b is, or B star, sorry, is in the column space of A, we know there is some vector x star such that ax star equals b star. And this should not be surprising. Notice that the dimension of the null space of A is 0, so really any vector will do. So we'll call this vector x star. And through the transformation A, we can map this point x star to this point right here, b star, using the transformation A. So x star gets mapped to b star. Okay. We also know that b star is the closest output, and we know that because of the fact that we're dealing with projections, and just by construction, this projection is the closest r, or the closest vector to b I can find. And you can play around with the applet that I showed you in the section 1 of the lesson. You could choose any other vector in here and try and draw a residual, and you would see that that magnitude of that residual is going to be greater than the one that I've just drawn. So play around with it and convince yourself that this is true. Okay, so the question that remains is I still need to try and figure out an equation. So you need to find an equation that minimizes r, or the magnitude of r, using info we know. And this is the hardest part. All we know is A and B. And what we're doing is we're trying to figure out how to find this x star that solves, that minimizes this residual. Okay. Well, we know a few things. And so this is we're almost there. So since B star is equal to the projection of B onto the column space of A, we can say that alternatively and better, B star is equal to AX star. And X star is, I haven't defined it yet, is the least square solution. And from vector properties, the other thing that we know is just vector addition. We know that B is equal to B star plus R. And so if I solve for R is equal to B minus B star. Well, I know what B star is relative to A, so I'm just going to make this substitution here. So B star is equal to, R is equal to B minus AX star. All right, so this is where we need a little bit of cleverness, because we still are missing a key piece of information. There's still something that we just don't know. We don't quite have enough information to really solve this. So what we're going to do is we're going to use this concept of what the null space does. So remember back in several lessons, the vectors that live in the null space of A, so are x's that solve AX equals 0. Okay, and so what that means is any vector x that lives in the null space of A, if I multiply that by A, I get 0. So x just gets mapped to 0. It gets annihilated. AX equals 0. Well, I could also say something similar about the vectors that live in the null space of A transpose. So what I'm going to do is I'm going to change the variable, because otherwise it gets very confusing. And I'm going to say that the vectors, all the vectors just collectively in the null space of A transpose are the vector y. So y is my general vector. So the null space of A transpose then contains y's that solve a similar equation. So the question is, what is that? Well, in order to map from the input vector space to the output vector space, I run it through the transformation A. In order to run the transformation from the output vector space to the input vector space, I'm going to use a different matrix. And if you're thinking it's the inverse, that's not true. We're not running this equation. We're not running this the transformation backwards. We're just going to try and we're trying to map from Rm to Rn now. And the way that I do that is I use A transpose. That's why A transpose shows up so much. So the null space of A transpose then contains the y's that solve A transpose y equals 0. And so anything, if I'm mapping from from Rm to Rn now, any vector that lives in the null space of A transpose gets annihilated and it gets sent to 0. And notice that R, my residual, is in the null space of A transpose. So R is is a particular vector y. So all I'm going to do is A transpose y equals 0. This is just a fact of life, just a property of the null space of A transpose. Okay. And y, or R, is in the null space of A transpose. So R is just an example of y. So A transpose R would equal 0 as well. And I just so happen to have an equation for R. So A transpose B minus AX star equals 0. And now I just need to do a little bit of algebra here. A transpose B minus A transpose AX star equals 0. Notice you have to be careful with the A transposes here. All right, and now I prefer to have my what I'm solving for on the left-hand side, so I'm just going to rewrite this as A transpose A X star equals A transpose B. Okay, so the last dangerous thing you have to do is figure out how to solve for X star. And don't divide by A transpose A, that is bad. So what we need to do is we need to use inverses. So to undo matrix multiplication, we use inverses. And we're not going to do this one at a time, we're just going to do it all in one shot. So everything that is multiplying X is A transpose A. So I'm just going to multiply both sides by the inverse of A transpose A. So here we go. A transpose A inverse A transpose A X star equals A transpose A inverse A transpose B. Okay, so A transpose A inverse is, of course, by definition, an inverse of A transpose A. So all of this stuff on the left-hand side cancels. And so what you are left with is X star is equal to A transpose A inverse A transpose B. And this right here is your least square solution. So X is your least square solution. And we know B, we know A, and we can get A transpose from A, and so we have everything we need on the right-hand side. Okay, so the next exercise is going to ask you to code this in MATLAB using an example that you have a solution to. So good luck.